Okay, great. I think we can start now. So again, welcome everyone. Thank you so much for joining us for this info session on the Master of Science degree in Physics with the Quantum Technology specialization at the Institute for Quantum Computing at the University of Waterloo. And today I'm joined by two speakers. We have Michael Grabowecki, who is the Quantum Technology Lab lead for this program, and Zuan Yang, who's a master's student who graduated from this program. And they'll be sharing about it and letting us know why it's such an amazing program. And I'll pass it on to them to kick us off.
Thanks so much, Taku. So welcome, everybody. It's fantastic to see so many of you coming in from all around the world for the information session today. Hopefully, I can give you a little bit of a perspective of what this program is all about and what we're trying to do here, and encourage you to apply. As Taku mentioned, my name is Michael Grabowecki at the Institute for Quantum Computing. I am the Quantum Technology Lab lead. What that essentially means is that I am responsible for kind of the day-to-day operations of this program, or at least the hands-on component of it. I've built out a teaching lab that's predominantly been designed for this program and is now kind of been expanded out to other IQC activities and TQT events, TQT being the Transformative Quantum Technologies Research Initiative here at the university that helped fund kind of this lab space for the program. So my day-to-day is to basically deliver the content for this program and develop out the curriculum. And then also with us today, as Taku mentioned, we have Zioan, who is one of our recent graduates from the program. Maybe Zioan, you want to just introduce yourself briefly?
Yeah, hi everyone. So welcome to here, and my name is Ziyuan Yang. So I'm master student in quantum technology program at University of Waterloo, and also I finished my undergraduate study in Waterloo, as a major in the physics. So I'm so happy to share my experience today. So nice to meet you all.
Perfect. Thanks so much. So she'll be available to ask questions. We'll have a bit of a Q&A session at the end of this, so you can direct questions to her or to myself, depending on what's more relevant. But okay, so let's get started, right? So let's talk briefly about just what the Institute for Quantum Computing is at the University of Waterloo. And this is a kind of a massive multidisciplinary institute focused on quantum information processing. So it spans two or even three, you can argue, buildings on campus, one being the Quantum Nano Center, which you see on the left, and the other two being kind of the research advancement centers split between two buildings on the right. IQC has a huge amount of individuals that are based in both of these buildings. The lab that I have developed out and run for the program is in the Research Advancement Center. And this institute has more than 30 independent research groups in it, right? And those research groups span over 7 different UWaterloo departments. So it's incredibly multidisciplinary. So we have principal investigators from chemistry, from computer science, from mathematics, from physics, and I'm forgetting a bunch more, but there are a lot. Engineering is another big one. And so this is a highly multidisciplinary program or institute. We kind of celebrate that here. We have over 400 members, all researching the goal of kind of furthering quantum information processing research, and having a number of members that high means that you can kind of always find somebody that is an expert in what you need to do for your research, right? If you're stuck in a particular area, there's somebody nearby that can help you out. And so there's a lot of networking and collaboration opportunities here. In terms of the Master of Science in Quantum Technology program that we offer, it's just one of the many graduate programs that IQC offers. This is the only course-based program in physics that we offer as a master's degree. And what it is a one-year course-based program with a really strong focus on hands-on experience. So the idea here is that we get you in the lab and you work hands-on with industry relevant and research-relevant quantum devices. And we do this over a set of laboratory courses, so dedicated experimental courses. The first is in something called coherent control, and we deliver that using spin systems. So we introduce quantum information processing through spin dynamics, using nuclear magnetic resonance, as well as nitrogen vacancy centers in diamond. In the winter term, we offer a course in experimental quantum optics. So we look at photonic quantum technologies, how photons are used for quantum information processing applications. And lastly, in the spring summer, we offer a course in superconductivity and low temperature quantum devices. And in that course, we focus on all the components that go into building the a simple superconducting qubit architecture, and we capstone the course by you actually cooling one of those down and doing some quantum control. In addition to these core experimental courses, you'll also have an opportunity to conduct independent research. So one of our courses in the course-based program is a research term where you'll partner up with one of the principal investigators at IQC and work on your own research project in their lab. And that gives you kind of a perspective into what research will look like at the Institute for Quantum Computing and UWaterloo more broadly. And of course, when you do that, and throughout the program, you're joining this community of 400 plus quantum researchers. So your quantum network is going to expand quite drastically, and you'll always be able to collaborate with the people around you. And the last thing I'll kind of mention here is that there is scholarship funding available for successful applicants. So there, you'll have potentially some support if you're accepted to the program. And the application deadline for this year for September 2026, yes, that's right, start is January 9th, I believe. Yes, it was blocking it for a second there, sorry. So yeah, please, this is the right time to be thinking about whether you're applying, and I encourage all of you to submit an application. In terms of what the goals of this program are, of course, you might think, oh, I'm going to be an expert in quantum mechanics by the end of 1 year. And of course, there's no real 1-year course-based master's that can make you an expert in quantum information processing. So that's not really the goal we're aiming at here. The goal is more to get hands-on experience with quantum information processing and to develop a kind of quantum literacy or a breadth of knowledge that you can use to apply to quantum problems as you move forward in your career. So this program really establishes a tool belt. It says, you'll leave the program with a set of skills that you can use to solve quantum problems, whether that be in the quantum industry or in a high impact PhD program in experimental physics, or even a transition to a theoretical PhD. So as part of this program, you don't just do hands-on experimental courses, you also take the same theory courses as the other graduate students at IQC would take. So you get the theoretical foundation as well as this experimental experience. And of course, you'll leave with the familiarity of all these quantum devices. So we pride ourselves in this teaching lab where we've built out we haven't skimped on kind of the quality of the devices you're working with. All of the devices you interact with are research grade, meaning that if you take a course in experimental quantum optics in this lab, you're going to, and eventually research quantum optics, you're going to see a lot of the same devices on the table. And so you'll have that familiarity kind of throughout this program. I already mentioned kind of the networking opportunities. It's just kind of listed again here. And the goal of the program is a PhD prep program to get you on the way to having a really high impact PhD in quantum information processing. But we don't want to limit it there. We also want to have a program that opens up for transitions to industry directly out of here. And we're kind of seeing this shift in the quantum industry where a lot of these quantum companies are becoming bigger and bigger. And all of a sudden, there's less of a need for companies to hire a PhD graduate or a postdoc graduate that's hyper specialized in a particular thing. And instead, what they're starting to look for is just individuals with a quantum literacy that can be hired on at an entry-level position in quantum and grow their career there, having this tool belt that a program like this offers. And so that's really the goal of this type of program and the one that we're offering here. And in terms of who should apply, I really would say anyone interested in starting a career in quantum or even preparing for, further education in quantum. And all backgrounds are welcome. So just like IQC is incredibly multidisciplinary, so too is this program. We have accepted students from, applied math, physics, chemistry, computer science, engineering, nanoscience, the list goes on. There's really no specific technical degree that we're expecting here. We just want, some sort of a good working knowledge of linear algebra. And that doesn't even have to be specific to quantum, right? If you're good at or experienced with linear algebra, you can succeed in this program. And that's just because quantum mechanics is inherently kind of a linear algebra-based theory. So it helps to have this good foundation. In terms of the career trajectory, so what are our graduates actually doing now that they're finished with their degree? As you might expect, a lot of them are working on PhDs now in quantum, either at UW or at other institutions. But in addition to that, we're seeing that quite a few of our students are working more in staff roles or in research roles that aren't directly student, right? So working maybe as research assistants or research scientists in the research groups kind of locally and abroad. And also transitioning to industry. So we're seeing some students kind of becoming lab technicians at universities or in research groups, and even starting their own companies or moving to work for quantum startups. So it is by no means limited to just PhD prep. We have just even the 3 students with testimonials that you're seeing on the screen here. Each of them have kind of taken a different path, right? So Raul on the left there, he's now pursuing a PhD in biomedical engineering with a focus on quantum sensing. Tejas is working as a research scientist in partnership with the Canadian government at the Quantum Valley Ideas Lab on navigational tools using quantum sensors. And Zach St. Pierre on the right, he's now working as a lab technician at the University of Southern California, focusing mostly on quantum optics. So you can see that, this is just a small subset of the students, but kind of a breadth of career trajectories just on the screen here. And one other kind of testimonial I want to draw your attention to and is kind of highlighted on the course website is Grant Brassams. And he, I think, summarizes the point of this program really well, where he says, I got hands-on experience with actual software platforms used to run modern laboratory equipment and simultaneously got a strong theoretical background to do the work. And the best part of the program is that it gives you that foundation to further your career in academia or specialized lab work or even industry. And that really sums it up, right? This is the whole point of the program. And you can read more about his specific experiences on the course website. And I think at this point, Tucker, you wanted to just prompt or ask a couple of questions for Z1.
Yeah, thanks, Michael. We have a past student from the program here, Z1, and she's going to answer a couple of questions. So my first question is, how did your time on the program and what you learned help you prepare you for your current career and just your general academic path?
Yeah, I think before starting the program, I wish I had known that you don't need to be an expert in any quantum platform to do well. I used to think I need to strong experience in superconducting circuit or optics, but the program actually teaches you everything from the basics. And for me, the biggest challenge wasn't the application itself. It was getting used to the fast pace and the hands-on style of the program. You move quickly from NMR experiments like pulse control and spin echo measurements to quantum optics and then to superconducting devices. What really helped was being honest about what I don't know. Asking a lot of questions and using the support from the instructors. Once I realized that the goal is to learn by doing and not to be perfect right away, it become much easier and much more enjoyable. Yeah.
Thanks so much, Z1. That was great. I think, Michael, you can carry on now.
Oh, okay. Sure. Yeah, so now that we've talked about again of what the program is, what the trajectories are, what people are doing as graduates, let's actually talk about the program a little bit more detail. What's the substance of the program? And really, from my perspective, what it comes down to is these three core experimental courses, that'll happen in the lab. And the first is a course called QIC 860. And it's labeled Lab on Control of Quantum Technology. And we really emphasize that this is a focus on the control of quantum technology and not on any specific platform of quantum technologies, right? So we use spin-based systems in this course to kind of deliver the content, but the content itself is very portable to other modalities of quantum information processing. And we're really just using the spin controls as a test bed for quantum information processing. So what we cover here is we use nuclear magnetic resonance spectrometers as well as nitrogen vacancy centers in Diamond to essentially introduce pulse programming and gates, sequencing a quantum experiment or an algorithm. We explore the decoherence or the loss of quantum information in any real quantum processor, and we explore decoupling sequences or ways to control these interactions with the environment and preserve the quantum coherence as long as possible. And then we move on from there and we explore quite a few quantum information processing applications. So we look at quantum simulation, something like randomized benchmarking. We look at quantum sensing introductions. And the list goes on. And we learn as well a bunch of important quantum gates like CNOT gates, Hadamard gates, how to implement them in the lab. So all of these techniques and concepts are not specific to NMR, not specific to spin systems, but are portable to basically any pathway to a qubit that you can imagine. And that's really the point of that course. The second course that we teach is a lab on photonic quantum technology. And so this one is a little bit more specific to how photons translate to quantum technologies and what the benefit of using photons for quantum information processing is. So we explore kind of a wide range of topics that are most relevant to photonic applications. We spend time on quantum state tomography and process tomography. So, given an unknown quantum state or something you want to characterize, what is a targeted set of measurements you could do to reconstruct that state? Given an operation, quantum operation that's happening to your qubits, how do we prepare different quantum states and measure them in such a way that we know what that process is doing? We explore photon counting and photon statistics. So we look here at, how do we characterize the performance of our single photon detectors that we're going to use to measure our quantum system, and how do different types of light sources behave? What are the differences in statistics between a classical light source versus a purely quantum light source? We also explore two-photon entanglement here. So we have an entangled photon source of single photons that we use to explore concepts like remote state preparation and entangled states, as well as violation of the Bell-CHSH inequality, which was kind of the first experimental demonstration that classical physics could not describe quantum correlations. We also look at both single photon and two photon interference, which are purely quantum mechanical interference effects, and how they have applications to quantum metrology and quantum sensing by enhancing the phase resolution of interferometers. And so these are kind of the things we cover in that course, which are relevant to quantum technologies. And then lastly, in the final term, you'll take a course on low temperature quantum devices and nanofabrication. And this course, it's structured such that you learn the details of each of the pieces that make up a basic superconducting qubit architecture. So there you need to understand what a superconductor is, what the superconducting transition looks like in a particular metal. And then we move on to something like a Josephson junction, which is kind of the beating heart of any superconducting qubit. It's the nonlinear device that allows you to isolate two quantized energy levels. And we explore in a series of labs the physics of those devices in isolation. We also explore superconducting microwave resonators, which is used for qubit readout and for filtering and qubit systems. And then we put it all together. We bring all these components together into one device, and we measure a superconducting qubit and do some quantum control with it. And along the way here, the course has somewhat of an engineering flavor, right? We learn about microwave circuits, how to characterize a microwave network, how to perform measurements both AC and DC on low temperature electronics. And you get to work with actual liquid helium cryostats, two of which are in my lab and can reach a base temperature about 1.5 Kelvin. So 1.5 degrees above absolute zero. And then when we take the superconducting qubit, we put it in a dilution cryostat, similar to what IBM and Google use for their quantum processors, which reaches about 10 millikelvin. So much, much, much colder than deep space. And this is where superconducting qubits operate. So you'll learn kind of a breadth of knowledge from these 3 hands-on courses, in addition to having your own research term and theoretical courses to supplement. So it's a total of 8 graduate courses in the course of 1 year. And just kind of getting into a little bit of the details here, showing you a few of what the setups look like in our program. So for the spin dynamics or the coherent control course, we have 5 benchtop NMR spectrometers, which you see on the top right there. So the device on the very right that looks kind of like an oval, that is an NMR spectrometer, and there's a really large magnetic field internally to that box, zero field outside. We drop a sample in, and the spins, the magnetic spins in the sample will polarize to that magnetic field, and that's what we define as our kind of 2-level system, our quantum bit, and we can perform pulse sequencing and quantum gates to those spins and explore quantum information processing. The benefit there is that a lot of our labs will use the same software interface because we're using the same quantum device. And so you get a familiarity with the kind of the physical system, and you can really focus on just the differences in the quantum information processing that you're doing each week. In addition to these devices, we also have a series of experiments on nitrogen vacancy centers in Diamond. An example setup you can see on the left there. This one's quite opened up and not really in a state for, that it's in for teaching, but it's a prettier picture to look at. So here you're actually exciting the electron spins inside a diamond with green laser light, and you're polarizing them to a specific quantum state, a specific energy level, and then we can apply microwaves to rotate the quantum state or to create superpositions, and then we shine the laser on it again and look at how much red light is produced by those electrons in the vacancy, and based on the amount of red light we see, that's an indication of what the quantum state was. So you can see if you look really closely in the diagram on the left there, although there's a lot of green light on the screen, there's also a little dot of red light that's hitting a photodiode, and that's actually the electrons in the vacancy emitting red photons due to the excitation of the green photons. And so this is just another kind of modality that's spin-based for quantum information processing, and you'll learn a bit of quantum sensing with that type of device. In terms of the optics, just have a small sampling of the setups that you'll encounter in the lab here. These 3 setups are actually focused on the entangled photon lab. So on the left there, you see the entangled single photon source, sorry, which is arranged in what's called a Sagnac interferometer. And the idea there is that depending on the polarization of the blue kind of input light here, the photons will have to make a quantum decision of whether they'll reflect or transmit off an optic. And because you don't know which one it chose, because it was a quantum decision, it effectively goes both ways at once as a superposition, and this is how we prepare entangled states in 2 photons. And we send one photon to one person, Alice, and then the other photon to some other person, Bob, and we can do correlation analysis on their joint entangled state. And that correlation analysis is done with the device in the kind of the top right there, which are called polarization analyzers. And then we couple those to single photon detectors and examine kind of the entangled correlations we get. In the bottom right, we have a polarization Michelson interferometer. This is used to explore remote state preparation of entangled states. So you'd pass one photon through the interferometer, and you would measure the other one somewhere else. And based on the measurements done somewhere else, it'll change the interference effects that you observe in the interferometer. And so this is really showing that, these 2 measurements from the 2 parties are correlated together, right? And we see an experimental demonstration of that. And then lastly, we have this course on low temperature quantum devices. So on the left here, you see kind of this chandelier looking device, which is very similar to, IBM or Google's press releases where you see, the depiction of a quantum computer, right? And this is what it is a cryostat, right? And each of these kind of gold plates, as you go down, will be at a fundamentally different temperature, and it would decrease as you go down plate by plate. And what this system uses is a mixture of helium-3 and helium-4 in a kind of a closed loop cycle with vacuum pumping. And that, through a series of heat exchangers, delivers cooling power to the qubit, which would sit kind of right at the base of the cryostat. So it's a huge device that really is just meant to cool the qubit, which is a relatively small device at the very bottom, down to basically 10 millikelvin. So extremely, extremely cold temperatures. And the systems that you see on the right there, the top one is one of the liquid helium cryostats in my lab. This is a flow cryostat, so it uses helium-4, and basically the vapor that flows over your sample is what produces the cooling power, and it has its own kind of liquid helium reservoir. That it can draw from. And that reaches a base temperature of about 1.5 Kelvin. So this is sufficient to kind of characterize a lot of the low temperature devices that comprise a qubit, but not quite cold enough to characterize the qubit itself due to how you need to control a qubit. So you'll get familiarity and usage out of kind of both of these types of cryostats and learn a whole bunch about microwave engineering and low temperature devices and nanofabrication and all that along the way. And so that's kind of my little spiel about each of the hands-on courses and what you'll interact with. As you can see, like this is all actual research grade equipment. The dilution cryostat on the left there, that's $1 million device. You don't see those growing on trees, right? And it's great that we have this program that can offer teaching capabilities and hands-on experience with a device like that. And with all that said, I think we should move maybe to a question and answer period where, if you have any questions about the program, what you'll learn, what the details of the application stuff, you can direct it at me. And if you have any kind of experiential questions, how was it to do each one of these things, you can ask Ziyuan as well. And maybe we open up the floor.
Thanks so much, Michael. So there's a couple of questions in the chat already, so I'm just going to start with those.
Sure.
So the first question, let's just see here. Still scrolling. Okay, so Kanjan asked, does the independent research give students the opportunity to write a thesis?
So it won't be a full-fledged thesis because you're not doing like a full graduate degree in research base. So you're not defending a thesis here, but what we have is kind of a miniature version of that. So you'll write a report based on your research term, and you'll present that to the other PIs that are kind of supervising students in this course. So you kind of do a mini defense, and you do write a report that you submit and kind of take with you at the end of that research term.
Great, thanks for that. And then Nena asked, is the research opportunity guaranteed, or is it like a co-op?
So the research opportunity is not a required course for the program. It's an option. To date, pretty much every student that's gone through the program has opted to take that research term. It's a great opportunity for you. It does depend on you kind of talking to a professor on campus and making sure that they're okay with you joining their group for a term. But so far, the reception from IQC faculty has been very good, right? So typically when a student wants to work with a professor, they haven't had a lot of trouble making that happen for that term, as long as you give a little bit of notice.
Okay, and then just 3 more questions from Kanjan. So first question is, he said students can transition to theory afterwards. How many students have been able to do this?
Yeah, that's a good question. So I know of a few that have been interested in, for example, the Perimeter Institute for Theoretical Physics as kind of graduates from this program, and they have made that transition. It is definitely a lower percentage than those that pursue experimental after this program, and that kind of makes sense. This is an experimentally focused, hands-on kind of program. But I'd say, there's a decent percentage, and I don't have like an exact percentage for you, but I know that some students have actually made that transition.
Okay, great. Next question, is there a cutoff for applications GP-wise for this program?
Sorry, can you say that one more time?
Is there a cutoff for applications GPA-wise or like grade-wise for this program?
Yes. So in terms of, the prerequisites of the requirements grade-wise, it's the exact same as all the other IQC grad programs. So I think it's a 70% average or 70% GPA in undergrad. There's no difference between the requirements of this program and the requirements of the thesis-based programs. And I think the specific details of this are on the program webpage. Is that right, Taku?
Yes, it is. And we'll be sending out an email to everyone. So we'll answer some of those questions in details and like send you links to stuff.
Yeah.
Okay. And then the next question is, do you have a sample course sequence for the 3 terms? And are there any electives?
By course sequence, do you mean like which courses are offered or required for the program? Is that kind of...
Yes, I think so. Like for the 3 terms, like how many courses maybe you're taking each term, and are there any electives in those courses? Yeah.
So definitely there is a list of the courses that are offered and are required for the program on the website. Like I said, it's 8 courses within the span of 1 year. 3 of them are the hands-on courses that I talked to you about. One of them can be the research project, so that's an elective you can choose, and most people do. That leaves 4 more, right? 2 of which are actually, I think 3 of which are required courses by IQC in the physics department. So you'll take quantum mechanics through the physics department, and then you'll take a course called QIC 710 and QIC 750, which are the quantum information processing mandatory courses that IQC offer to all grad students that join IQC. So you're left with 1 course, assuming you do the research elective, you're left with 1 course that you can kind of take as an elective and choose something that's based on your interest.
Okay, great. I see, Javier, you've asked, could I apply and join to the master with my actual degree, or do I need to revalidate the studies that I already have? So I'm assuming that you have a master's program, a master's degree, or you're currently in one. I'm not sure if you can answer that question, Michael.
If I'm understanding right, it's, if a student has a bachelor's degree and already has a master's degree or some graduate degree and wants to take this as an additional graduate study, that's no problem at all. This only would strengthen an application to this kind of program, right? You'd say, I don't just have my undergrad experience, I also have my performance in a graduate degree that you can base the merit of my application off of. So certainly, like, we don't reserve this only for recent bachelor's graduates. It can be anyone.
Okay. And so another question is, what does a successful applicant look like? I know you've covered that, but maybe just once more.
Yeah, I think a successful, like what I hope a successful applicant would kind of bring to the table is just, a little bit of demonstrated understanding of linear algebra and, a good performance overall. Like we're looking for people to meet the IQC requirements of GPA, but we're also looking to see if you have, a good track record of just knowing your stuff a little bit with linear algebra. Having a bit of a quantum background will help you out, and we do kind of see that in more successful applicants. But it by no means is a requirement that you've taken, 5 quantum courses before coming here. It really just is, have you done a technical degree as your bachelor's studies, and how did certain courses in that go, right? And that's kind of, in addition to your references, you always want to have solid references when you're applying to any graduate program, and those are weighed quite heavily in the application review.
Okay, great. And I think I want to ask this to Ziyuan. So the question is, how much of a workload is the program? Roughly how many hours per week do students typically spend on the labs and assignments?
I think because we have the 3 terms and the 3 term, as Michael said, we have the 3 different lab. So I think in the country lab, this is the first term lab. So we learn the post programming, Han, Echo, and corporate gates and NV center sensing and working with up the 3-qubit samples. So maybe I think the 1 week maybe spend 3 to 4 hours in the lab, and after lab you can read the report and do some preparation for the next lab. It's feel free for it's free for you, so it's up to you. I think need not be there. You have the more time to learn the course because one term we not just have the lab, we have the another course, 1 or 2. Yeah, so it's for free. So the next term we have the photonics lab. So we will do the HOM interference and Bell CHSH tests and full quantum state and process tomography. I think maybe spend a little more time, but it same as before, I think. So at the last term, we have the low temperature lab. I think this part is very interesting, and we will working with the superconducting transitions and Josephson junctions, and the resonator, and even Transmon qubit spectroscopy in cryogenic systems, and maybe spend 10 hours 1 week, I think. So it's for free. But I think this you need to more preparation for the lab, I think. Yeah, because read the book or read the note, yeah, that's more useful for you. If you preparation is good, so in the lab you can easier to do. But if you preparation not good, so you maybe spend more time to do that. But no worries because we have the Mako. Yeah, Mako will be yeah beside our so it's easier. The instructor will help you. Yeah.
Thanks, Yuan. And then there are a couple of questions in the chat. But there's one I'm seeing. There's a little bit of confusion between course-based and thesis-based. So I was wondering if you could just simplify that for everyone.
Sure. Yeah. So IQC offers both thesis-based and this course-based option. So if you're doing a master's in physics, you have the two options. In quantum information processing, you have the two options. You have a thesis stream, and then you have this course-based stream. The thesis-based stream would be you would take like 4 grad courses, and then you'd have a dedicated research project in one of the groups of the PIs at IQC. And the focus there really is, you're defending a thesis at the end of it, right? Whereas the course-based masters, it's half the time, so it's 1 year versus 2 years, and the focus is on getting you hands-on with quantum technologies and really getting the theoretical and experimental foundation that you need to kind of move on to a PhD or to the industry. So in, I guess, the course-based, you don't have a dedicated research project except for that research term. Whereas the thesis-based, if you apply for it, you have an overarching big project that you're working on, typically a single big project for a master's studies, and then if it's a PhD, you'd have many projects that you're kind of doing over the course of 5 years. So yeah, there's quantum information specialization for thesis-based programs at IQC, and then there's the quantum technology specialization, which is the course-based.
Thanks so much for that response. There's still a couple of questions. I know we have 2 minutes left. So I'm going to cherry pick a couple of them. I'm seeing here there's a question on, is the course up to date with all the latest techniques for creating different kinds of qubits?
I would say yes, with the caveat that, of course, we're trying to teach this from the foundation up, right? So you might not have the most complex research setup you can imagine on the table, but the devices and the electronics and everything and the actual physical, quantum devices are actually, research grade. Right? So we might have a more simplistic control scheme, for example, than you might find in Chris Wilson's low temperature lab that has, a stack of 10 AWGs all doing different things, right? So I would say we introduce all of the relevant techniques and concepts, and then you can take that and apply it to a research setting where maybe you have the same devices, just more of them, or maybe connected in a slightly different way. So yes, it's relevant and modern, but no, it may not be the equivalent one-to-one to what's in a research lab in terms of the complexity of the setup.
Okay. And then there's a question on whether the degree assists in getting technical work in the semiconductor industry, and not just at IQC.
I think that this program doesn't just set people up for a career at IQC. And we've seen that with a lot of how our students have transitioned, not just to U-Waterloo positions, but also to external positions, both in industry and in academics. In terms of specifically the semiconductor industry, I can't speak to exactly what every student that's gone through the program is now doing. It wouldn't surprise me if a couple of them have gone into kind of the semiconductor industry, but I don't have like a number or I can't tell you that X many have actually made that transition, if that makes sense.
Yeah, thanks for that. And then the last question, just on scholarships, and is it a full scholarship? How many students typically get a scholarship?
Yeah. This is yeah. So the funding, there's kind of a big pool of money that IQC, TQT would put forward, and we would make this kind of a merit-based distribution of those scholarships. So typically it's not a full ride, but it does depend on kind of the strength of the applications, and some students might get a larger number of amount of scholarship than the others. But we try to make sure that most students that are accepted in the program get a little bit of financial assistance. But I can't guarantee that it'll be everybody and guarantee an amount to everybody.
Great. There's still more questions coming in, so I just want to just quickly try to get these in. There's a question on if we have career fairs or opportunities to meet with future employers, and then also how long has the program been running for?
Yeah, so that the last bit of that is this is our 5th year of operation. So we have our 5th kind of batch of students coming through the program right now. In terms of the career fairs, you're basically as a participant to this program, you are an IQC member, and therefore you have access to any and all events kind of happening at UW and at IQC specifically. Often we have outreach events where companies or industry can come in and kind of give a presentation to the group of IQC students, as well as kind of guest speakers that are coming in from industry that you can kind of engage with. So just being a part of IQC in general enables you to kind of participate in all of these events that happen throughout the year. So yes, you'll have opportunity to kind of network in that way.
Okay, awesome. Thank you so much, Michael and Ziwan. This was a great session. So many questions, and we will send an email to everyone after the session, possibly by Friday. Just answering some of those questions we didn't get to, like admission stuff specifically. But also here on the slide, we have like contact information for people to contact for specific questions. So admissions will be Paula for science admission, because you will be admitted to the Faculty of Science. You can email Holly, and then for anything to do with the course and the labs, you email Michael. And there's just general support with your application would be the grad apply email. But yeah, thank you so much for joining us today. And we hope that you'll be applying for this program, and have a great rest of your day.
Yeah, please
Thanks,
don't
everyone.
hesitate to email your questions if they didn't get answered today. Thank you all for joining. I really hope to see your application.
Yep. Thank you so much, everyone.
you.
And please feel free to send us emails asking any questions at all. No question is silly or too small. So yeah.
Yeah.
And thank you for
very
the
much.
feedback on the website. Whoever put that in, thank you. If you have any more notes on that, please feel free to let us know.
Yeah, fantastic. All right.
Yes.
Thank you.
Okay. Bye, everyone.
Take care. Okay.